In this lecture, we are going to continue our discussion about the distributions of returns and log returns. As we saw previously, one problem with fitting the normal distribution to returns is that the returns have much heavier tails than the normal distribution would predict. So perhaps the normal distribution is not such a good assumption. Now, as an aside, let me say that, although this is evident, the normal distribution is still widely used as a model for returns in finance, so don't be surprised when you see it, even at very high levels of study. Well, one thing we can do is ask ourselves, do we know of any distributions that look like what we saw? We saw a bell curve, but with heavy tails. In fact, one well-known distribution that's shaped like a bell and has heavier tails than the normal distribution is the t-distribution. The t-distribution is famous for its use in one of the most commonly applied statistical tests, the t-test. So what is the t-distribution? Well, as mentioned, the t-distribution is a real value distribution that goes from minus infinity to plus infinity and is shaped like a bell curve, but with heavier tails than the normal distribution. In fact, if you look at the equation for the t-distribution, you can see that it has polynomial tails. That is, the probability density drops off as a polynomial function of x. This is opposed to the normal distribution, where the probability density drops off exponentially with the negative of x squared. If you're mathematically inclined, you should be able to see this right away. Otherwise, if you are intimidated by equations, you might want to go through this more slowly in order to get a better understanding of what I just said. Note that in its usual form, the t-distribution has only a single parameter called nu, which refers to what is called the degrees of freedom. It's kind of a strange name, so don't worry about it too much. It's a parameter, just like how mu and sigma are parameters of the normal distribution. In this usual form, the t-distribution must always be centered at 0, which seems somewhat restrictive. In practice, we can extend the t-distribution so that it has location and scale parameters. That is, we can move the center left or right, and we can make it fatter or skinnier. Of course, it's a little more complicated than the normal distribution, since we also have this parameter nu, which also controls how fat or skinny the distribution is. In fact, the formula itself isn't very important for us, since we can't estimate the parameters of a t-distribution in closed form anyway. This is unlike the normal distribution, where mu is just the sample mean, and sigma squared is just the sample variance. Instead, it's more like a machine learning model, where we specify that our model is a t-distribution, and then we call the fit function, which finds the parameters that best fit the data. You might guess that this uses maximum likelihood estimation. After calling the fit function, we get back the degrees of freedom, location, and scale parameters of the t-distribution, which we can use later for drawing PDFs and QQ plots and so forth. And by the way, note that if you standardize the random variable by subtracting the mean and dividing by the standard deviation, passing that into the t-distribution with location 0 and scale equals 1, that's equivalent to calling the t-distribution with the same degrees of freedom and the given location and scale parameters.